So, like always, our slides are from CS 188 of UC Berkeley. Okay. So we continue our topic on CSPs. Now we are going to talk about some efficient solutions for CSPs and we'll talk about local search. No, I don't know इतनी दूर पहुंचेंगे कि नहीं पहुंचेंगे, but लास्ट स्लाइड कंप्लीट हो गई थी ना आई थिंक. Right. So we were talking about CSPs. And remember this problem? Will there be any problem in this case? If I want to color this, if I want to color this graph with these domains, will there be any problem? Yes, will there be any problem if I start solving this one?
Yes.
What will be the problem? Right. Anyone else? Anybody who says there will be no problem? So in this case there will be no problem. This can be given red, this can be given blue, and this can be given green. Right? So this case is clean. There is no issue in this case at all. Problem would be when domain is just 2, right? That will create problems for you, because even though all the arcs are consistent, but taken these three things together, it won't be consistent. So that thing will not be 3 consistent as we'll see. CSPs are variables. So we have talked about variables, we have talked about the domains from which variables take values. We have talked about constraints, okay? They can be explicit, implicit, and so on. Goals, find any solution, also find all, find best, etc. So this is something that we have been seeing throughout the course. अभी तक अपन ने इसमें कुछ भी नया नहीं ऐड किया है, okay? We are just making it much more specialized. So we have talked about this before. Now, general purpose ideas give huge gains in speed, but it's all still NP hard. Now I think it's the right time to start talking about what is NP hardness. So what is this problem? What is the problem of P versus NP? यस कितने लोग ऑस्कलर्स हैं यहाँ पे? ओके, आ जाओ आ जाओ आ जाओ. So coming back to this, what is P versus NP problem? What is NP then? Not polynomial. Who said exponent? Okay. Okay. अच्छा, what is the closest you have read about this P versus NP problem? You know what is NP completeness? Can you name two NP complete problems? One is set. Okay. Now, what is the problem? What is the problem of set? No, but what is the problem? Question is, what is set? How do you frame that problem?
We need to find the assignment which will satisfy the given.
Say that again.
We need to find the assignment which will satisfy the given equation.
Right. Which satisfies the
Given.
right. So the way you formulate it is, we'll see. I'll state it. For which domain set works? देखो, if I give you a problem of this kind, x1 or x2 or x3 and x4 and so on, okay, this is a Boolean formula, right? This in itself may not be NP hard, but this problem in general, it asks this question that how should I put the values of these variables? If this is a Boolean formula, x1 to x4, they can take values from, their domain is 0 or 1, okay? So, if I put this equal to, if I put this equal to 1 and if I put this equal to 1, will this give me 1? Does it matter what I put x2, x3? Right? So, there will be instances when you will be able to look at the problem and tell for which assignments of x1 to x4 the problem is satisfiable. Satisfiable means you choose values of x1 to x4. In general, you choose values of all the n variables such that when you compute this thing, this will turn out to be a 1. It is said that this particular formula is satisfiable for those values. Is this a CSP? Is this a CSP? What I've just written? Now, so if you don't find this familiar, fine, but set was the first problem that was shown to be NP complete. So that's why it is important. Now, why are we talking about NP hardness in our case? Yes. Why are we studying NP hardness for our problem? What is our problem, by the way? This is awesome. So say that again.
We cannot find solution in polynomial type, but have a verifier which will verify any polynomial type.
But what is that? Right. Nice. So see, if this is the set of all problems for which you can have a polynomial time algorithm, right? Let's call that set as P. Can you give me 3 examples of problems in P? In P, knapsack, matrix computation, more, कोई क्विज विज है क्या कुछ? कब? 10 बजे? So then I will not do NP hardness right now. So let's continue with arc consistency, right? What was arc consistency? This is from previous class, so you should remember. देखो एक चीज that you need to remember and is useful for you in exams too, even though मेरी quiz नहीं है, but it will be useful in exams कि you remove from the tail. आप head में से कुछ नहीं remove करते हो, okay? That alone will clear 50% of your doubts जो भी exam में आएंगे. You have to remove from tail, okay? Now we have done enough examples of arc consistency in the last class. So arc consistency of an entire CSP. A simple form of propagation makes all arcs are simultaneously consistent. Now NP hardness इसमें role play करने आ जाएगा, but let me keep it simple. Is this arc consistent? In this arc, what is x, what is y? X is? So in this, we had seen a definition of arc consistency. In this case, what is x, what is y? X is v, NSW is y. Now, what was the case?
For each element in X, there should
For all in x, there should exist a y. Is this true for this? Right? So this arc is consistent. If I remove this red, is it consistent? No. Okay. Now, what about this one? Consistent? All right. What about this one? Not consistent because? For red there is blue, but for blue there is nothing, right? So in this case, what will we do to make it consistent? Delete blue. And this may create problems somewhere else. So once you delete, you have to run arc consistency again, okay? So that's why it's a costly operation, and we just keep on doing this. So this is not consistent and so on. So arc consistency detects failures earlier than forward checking. Important is, if x loses a value, neighbors of x needs to be rechecked, right? This is important. You must rerun after each assignment. This is what we have just talked about, okay? Tell me, is arc consistency sufficient? Will arc consistency guarantee you that you will be able to color well? Any example? We have seen this case, right? All individual arcs are consistent, but there does not exist any assignment for this graph, right? Are all arcs consistent? Yes, but there does not exist any assignment, because if you use red here, if you use blue here, this guy becomes empty, okay? What about this one? Is this fine?
yes.
This is fine, right? Because is this consistent? All arcs are consistent here, right? And we will have a solution to, let's say, use green here and use blue here. So this is fine. After enforcing arc consistency, you can have one solution left, can have multiple solution left, and you may not have a solution and you not know it, okay? So arc consistency still runs inside a backtracking search. Now K consistency. Now guys, I will need NP hardness, so I don't know where will I do it. I'll do it somewhere here itself then. Increasing degrees of consistency. So let me go back. If you have a quiz, you have a quiz. But anyway, so no NP hardness written here apart from the fact that it is NP hard. So if this is the set of, so give me examples of 3 problems which are in polynomial time set, which are in this set P. Linear search, okay. So linear search, I'll call it search. आगे कौन सी क्विज है भाई? परसेंटेज कितना है उसका? तो फिर हाँ. So one problem is this. What is next? क्लास के बाद मैं भी क्विज लूंगा, ठीक है? चलो सेकंड प्रॉब्लम. क्लास के बाद मैं भी क्विज लूंगा एक 5 नंबर की. हाँ चलो नेक्स्ट प्रॉब्लम. एक एग्जाम्पल इज लीनियर सर्च. व्हाट इज द अदर एग्जाम्पल? सर्च इज डन बाइनरी और लीनियर. मतलब तुम लोगों को सिर्फ सर्च ही आती है क्या? एक सॉर्टिंग. एनीथिंग एल्स? So, right, shortest path kind of things, Dijkstra's algorithm that you had seen, that runs in order. Right, at most order n cube. In fact, आपने जो भी problems algorithms में की हैं, they are all in P. Okay. So, wherever you are computing a time complexity and it is turning out to be of this sort, right, for a constant k, that's a polynomial time. So even if you have a problem that runs in this, it is still a polynomial time algorithm. Okay. Now on the other hand, so if this is your p, let me make this another set called NP. P is the set of those problems for which you have a polynomial time solution. If you have a polynomial time solution, can you verify it in polynomial time whether the solution was right or wrong? If you have a polynomial time solution to a problem, can you solve it in polynomial time whether my answer was right or wrong?
Yes. We directly use solutions.
तुम सबको बचा रहे हो, अब तुम चुप रहोगे. Yes, anyone else? Yes. ये साइलेंस देख के मैं इंडीड क्विज ले लूंगा, फिर जाते रहना तुम लोग वीसी के पास, डायरेक्टर के पास कि ये तो हमारे कंपोनेंट में था ही नहीं. क्वेश्चन इज, वापिस सुनना, if there is a problem that is in P, what does it mean? You can compute solution in polynomial time. My question is, can you also verify solution in polynomial time? कैसे? If you can compute in polynomial time, you can of course verify in polynomial time because you can compute it again. Right? So you can verify it in polynomial time. If I give you a problem, you give me a solution, I can verify it in polynomial time by computing again. So no big issues. Now, if I give you a solution to set, or forget set, if I give you a solution to our coloring problem, okay, can you verify it in polynomial time whether that coloring is right or wrong? right? But if I ask you to compute such a coloring, then no, right? At least we don't know any algorithm. That's what this P versus NP means. So you have a polynomial time set P, NP. NP is the set of those problems for which you said something.
We don't have solution which can compute in polynomial.
We don't know. So it's not that we don't have. We don't know of any algorithm that can compute these things in polynomial time. But given a solution, you can always verify that in polynomial time whether the given solution is right or wrong. That is the modern definition of NP these days. Okay. So what does NP mean? NP stands for non-deterministic polynomial time, and there used to be earlier definitions, they exist today as well, based on polynomial time Turing machine, deterministic Turing machine, non-deterministic Turing machines, but we are not going there. All we are saying is NP is the set of those problems, right? I mean, ye circle is wrong. NP is the set of those problems for which you can verify a solution in polynomial time. Given a solution, you can verify whether that thing is in polynomial time or not. Okay? Any problems that lie there other than set and coloring? प्रूव करो.
n cross n इसका सुडोकू है तो उसका सॉल्यूशन पॉलिनोमियल टाइप के कंप्यूटिंग सैट के अंदर ही आ गया बस.
राइट
सैट के अंदर आ गया सुडोकू.
राइट. कैसे करोगे? दैट्स अ गुड स्टेटमेंट. कैसे करोगे? जो बोला ना आपने कि सेट के अंदर ही आ गया. व्हाट डज इट मीन? Folks, I don't like this. Attendance कहाँ पे? ओके. सो जो क्विज की प्रिपरेशन करनी है, अटेंडेंस दो और निकलो यहां से. राइट. जिन लोगों ने को एंड इट्स फाइन, डोंट वरी, नो ऑफेंसेस, बट फटाफट निकलो यहां से. बाहर जाके पढ़ लो आधे घंटे. रिकॉर्डिंग्स विल बी मेड अवेलेबल. एनीबडी जो निकलना चाह रहा है, डोंट वरी, नो ऑफेंसेस, जीरो ऑफेंसेस टेकन, बट आई डोंट वांट दिस पिन ड्रॉप साइलेंस एकदम क्लास. कितने लोग, एक बार हाथ ऊपर करो, कितने लोग जाने वाले हो? आई एम सीरियसली सेइंग नो ऑफेंसेस. कुछ नहीं. ये नहीं होगा कि मैं बाद में कभी आपको बोलूंगा कि यार तुम तो वही थे जो चले गए थे. अटेंडेंस पे साइन कर दिया है ना? चलो. यू हैव 15 सेकेंड्स टू टेक योर डिसीजन. बाद में नहीं. अटेंडेंस लगा के जाओगे, बाद में नहीं बोलोगे कि अटेंडेंस रह गई थी. व्हाट डज दिस मीन कि वो एसिडी का पार्ट हो गया?
मतलब एसिडी क्या है?
कैसे?
We can form the given solution by satisfying a given substrate.
राइट
इसके अंदर जो ये होगा या constraint that we cannot have the same element in rows and columns
राइट
and then it is a solution.
राइट
So that's how it becomes part of it. But उसको अपने computing कर पाया कोई भी in the pseudo is very big.
राइट नहीं, यू डोंट हैव टू मेक इट वेरी बिग. रिमेंबर उसके लेवल्स होते हैं, इजी, वेरी इजी, हार्ड, वेरी हार्ड एंड सो ऑन.
मतलब अगर 2x2 सुडोकू है तो कर देंगे.
राइट,
But अगर
बट 2x2 सुडोकू उस वेरिएबल्स के साथ तो एग्जिस्ट नहीं करता. यू हैव टू हैव एटलीस्ट 3x3.
2x2 में 1 और 0 से तक एडजस्ट करना है.
1 और 0 से ओके राइट. हाँ राइट. अभी जितने लोग जा रहे हो मैं सबसे मार्क्स जरूर पूछूंगा बाद में, क्विज के बाद में. जल्दी करो यार, इतने से नाम लिखने में इतना टाइम कितना लग रहा है तुमको? कितने लोग हो गए नंबर? प्रॉक्सीज तो नहीं लगी है ना? हाँ चलो. All right, so now we have a class. Coming back to this, what is P versus NP? Don't worry, I'll make sure you gain something जो आपको एग्जाम में फायदा करेगा और उनको नहीं करेगा, even if they look after these videos. Yes.
P वो अपन निकाल सकते हैं solution भी वेरीफाई भी कर सकते हैं. फॉर एग्जांपल टाइम में P का
देखो, what is P set? All problems that you can solve in polynomial. What is NP? All problems that you can verify in polynomial time. You may or may not be able to compute them in polynomial time, compute the solutions. So will P strictly lie inside NP? Is this true? Right? So this is true. This is not the hard part for N versus P versus NP. Now, can you show that this problem in itself embodies a very big philosophical question, which is whether verifying a solution is as hard as computing a solution, right? Which we today believe that this holds. That means NP is strictly greater than P, but nobody has been able to prove it. So there is a set of problems called NP complete. Okay, those are those problems. So they are called, I mean, if you see factoring, okay, factoring or graph isomorphism, they lie somewhere here. They don't lie, they are not known to be NP complete, but they are not known to be in P either. So we believe they are somewhere in between. But if P is equal to NP, then those problems will fall into P. Now this is too much complexity theory. What I am just trying to say here is, these are the problems that you can reduce to each other. If you know set is NP complete, you can show another NP complete by proving its equivalence with set. This is called reduction. Again, I am not going there in reduction. All we are saying is there are more than 3000 problems known to be NP complete. Anyone, you give a polynomial time solution for anyone, this whole thing becomes one set called P. So NP complete problems are those problems for which exactly, so you give one solution to the you give solution to any one of them and all of them will fall into P. In fact, this whole NP set will fall into P. Now most of the problems that we talk about, they are all NP hard. Okay, remember CSPs की application की list आई थी यहाँ पे in the last class. Most of the problems, almost all there are NP hard. If I ask you this question, there is a graph G, okay, there is a graph G1, there is a graph G2. G1, so I am not saying this is no, okay. So there are two graphs given, G1 and G2. Graph G1, so if I ask you this problem, is G2, right? So first of all, let me talk about just graph isomorphism. What is graph isomorphism? Graph isomorphism is, given these two graphs, you have to tell me whether they are the same, right? आप उनके nodes के नाम change कर सकते हो. So in one graph you can have labeling as 1, 2, 3, 4. In another one you can have ABCD or something else. But essentially, if they have the same number of nodes, same connections as you had before, so then that problem is graph isomorphism. This is not known to be in P. This is not known to be NP complete either. Factoring problem that we use for cryptography, right? Computing multiplication of two numbers is easy, but factoring it into those two primes is super difficult. This property is used in cryptography. How do you use it? See, you take two large numbers, number 1, number 2. They are both primes. Let's say 100 digit. Now multiply them and get a number which will be roughly 200 digits. Okay? It is easy to multiply these? Yes. We won't do it by hand, but is it easy for computer to do this? But even for computer to be able to factor out that 200 number into these two primes, right, it will take centuries to do this. So that problem is hard too and is not known to be NP complete, but is somewhere in, but is not known to be in P either. So this is not a course on complexity theory. I won't go into this. All I want to make is just one statement. One, all NP complete problems, they are reducible to each other. They are polynomial time reducible to each other. You may write this down. What does it mean, polynomial time reducible to each other? Like he said कि if you solve set, तो sudoku भी solve हो जाएगा. How come? See, for set variables were x1, x2, x3, x4. Domain was something and you had to prove that equal to 1. For sudoku, what we'll have to do? All those blank spaces, put their variables. Domain will be 1 to 9. There is a constraint, something that should happen that looks exactly like this. Okay? And you know there are easy versions of Sudoku, more difficult and so on, right? So just let me verify if Sudoku is NP hard. आप लोग भी करो. Right. So it is generally known as the Sudoku problem is NP complete. Okay. What is the difference between NP hardness and NP completeness? That is a bit technical, but if a problem is known to be in NP and a problem is NP hard, then it is NP complete. So NP hardness is a even harder thing. Okay, I won't ask this it, so leave it. If a problem is known to be in NP and if a problem is NP hard, then it becomes NP complete. Okay, so that's why you don't have these problems as NP complete, because they are not known to be NP hard. They are in NP, but they are not known to be NP hard. Okay, how do you prove NP hardness? Reducing problems into each other. Problem 1, problem 2. You find a way to convert problem 1 to problem 2 and problem 2 to problem 1. Okay, but again, as I said, this is not a course on complexity theory. We are not doing reductions. Why is NP completeness important for our thing? Because we are going to talk about K consistency. What was 2 consistency? R consistency. Okay, what was 3 consistency? देखो 1 consistency, each single node's domain has a value which meets that node's unary constraints. So that's 1 consistency. 2 consistency is for each pair of nodes, any consistent assignment to one can be extended to the other. What about K consistency? What will be 3 consistency? K पे मत आओ, पहले 3 पे आओ. We have seen an instance of 3. What was the instance of 3? Remember that triangle? Right? उस triangle में 2 arc, R consistency was okay, but we had a problem with 3 consistency. एक बार इसको ढंग से पढ़ो. R consistencies for each pair of nodes, any consistent assignment to one can be extended to the other. That's what R consistency meant, right? Where arc is consistent, this means if you choose color this, if for X, you definitely will have a color for Y. This is what it means. What will be 3 consistency?
For 3 nodes collectively.
Right. So if you have for, let's say this is 3 consistency. 3 consistency will be for each 3 nodes, any consistent assignment to 2 nodes can be extended to the 3rd node. Was that true in this case? No. Any consistent assignment to 2 nodes. ये क्या अब? So any consistent assignment to 2 nodes does not extend to the 3rd one. Similarly for K, right? Give me an example जहाँ पे 4 consistency will be fail. Where will it fail if at all? It must be a clique. So it must be a complete graph of size 4. Okay, and so on. So K consistency means given K nodes, any consistent assignment to K minus 1 can be extended to the kth node. Higher K more expensive to compute. Okay. Why? What was the time complexity for R consistency, remember? Order n square d square, something like that tha. This will be even more expensive. What about K consistency? See, the more is K, complexity will rise very fast. Okay. For R consistency it was polynomial time. For 3 consistency it may still be polynomial time, but it will increase very sharply. For K, the problem becomes NP hard. So in general it will become NP hard for given. Now what happens for k equal to n? What is so special with k equal to n? You answered me this, I leave you to. I will not penalize you too much for staying back. Yes. For k equal to n, what happens? For k equal to n, this reduces exactly to the problem that you were solving. How will you define n consistency? एक बार बोलना जरा इस लैंग्वेज में. For each n nodes, which is your complete problem, any consistent assignment to n minus 1 can be extended to the nth node, and that solves your problem. Right? Sounds easy? Yes. What is the problem with this? It turns out to be NP hard. So the moment you have a problem to be NP hard, it ceases to have a elegant looking algorithm that will work for all the cases. Like if you have quick sort, it does not matter how bad array you give it, right? Worst case will be order n square. In this case, you can have easy problems that will admit easy solutions, but there will always exist such instances of the problem which you won't be able to solve in polynomial time for any algorithm. We don't know how to prove it, but that's what we believe. We believe NP complete problems are much more harder than the problems that lie in P. Okay, so I think I'll stop here, and tomorrow we'll start with strong K consistency. Attendance. Thank you.
So the rest.